Okay, let's begin with the first particle. In the initialization phase, the position of the first particle in the contour was established here. Now, what is its next position? This is how PSO responds. The velocity of each particle is updated using the following general equation. We can see that the velocity update equation combines the particle's previous velocity with influences from both its personal best and the global best positions. We customize it for the first particle in the first iteration and for both dimensions. Let's take a look at what this formula reveals. The first section retains the particle's previous velocity, allowing it to maintain momentum. What is momentum? Momentum refers to the tendency of a particle to continue moving in the same direction as it was previously. W is inertia weight. It determines the impact of the previous velocity of a particle on its current velocity. It helps control how much a particle continues in its current direction versus how much it is influenced by its cognitive and social components. A higher inertia weight encourages exploration of the search space, allowing particles to move farther from previous positions, while a lower inertia weight promotes exploitation, making particles more likely to converge on known good solutions. The second term, that known as cognitive component, specifically represents the influence of a particle's personal best position on its velocity. This component encourages the particle to move towards areas where it has previously found better solutions. The term p best minus x calculates the distance vector from the particle's current position to its personal best position, indicating the direction for improvement. C1 is cognitive coefficient that influences the attraction of the particle to its personal best position, or p best. It determines the strength of this attraction. Multiplying distance vector by C1 scales the influence of the personal best position. RND1 is a random number generated for each particle, typically between 0 and 1. The random factor adds variability, ensuring that particles do not follow a deterministic path, which enhances exploration of the search space. The third section is known as the social component. It influences how a particle adjusts its position based on the best known position in the entire swarm, known as the global best position, G best. This component encourages particles to move towards the best solution. The term G best minus x calculates the distance vector from the particle's current position to the global best position, indicating the direction in which the particle should move to potentially improve its solution. C2 is social coefficient, which determines how much the particle is attracted to the global best position. Multiplying distance vector by C2 scales the influence of the global best position. RND2 is a random vector generated for each particle. This randomness adds variability to the movement. It ensures that the movement is not purely deterministic and helps in exploring the search space more effectively. Both RND1 and RND2 are uniformly distributed random vectors between 0 and 1. After determining the new velocity values, it's important to check if they fall within the allowed range. In our problem, we set the range to -3 and 3. If the velocity exceeds 3, it is adjusted to 3, and if it falls below -3, it is set to -3. These velocity limits help maintain stability in the search process and prevent oscillations around optimal solutions. After updating the velocity, it is time to update the particle position. This update uses a formula. The new position is the sum of the previous position and the new velocity. After updating positions, it's time to apply position limits. By enforcing position limits, we effectively restrict particles to acceptable regions, enhancing the overall optimization process. In our problem, we set the range to -15 and 15. If the position exceeds 15, it is adjusted to 15, and if it falls below -15, it is set to -15. By incorporating dimensions, the matrix representation of the update equations can be reformulated as. Okay, now let's see how the first particle moves based on these equations. The first component of the velocity update is the momentum, representing the scale of the previous velocity. This value is shown in the contour plot here. The second component is the cognitive component. We need to generate random numbers to multiply by the cognitive coefficient and the distance vector from the particle's current position to its personal best position. However, since we are in the first iteration, this component is set to 0. The final component is the social component. Again, we need to generate random numbers to multiply by the social coefficient and the distance vector from the particle's current position to its global best position. The new velocity will be the result of the sum of these three vectors. Now, we can observe the process of combining these three components as a vector. Momentum vector plus cognitive component and plus social component. In this way, the new velocity value is represented here. Oh, wait. There's a problem here. This value is not within the allowed range. The allowed velocity range is between -3 and 3, so it needs to be adjusted. Okay, now the new velocity value will be shown here. By calculating the new velocity value, we can update the particle's position, which is current position plus new velocity This occurs here. In this time, the guard checks to ensure everything is in order. Yes, no problem. The new position value is within the allowed range. In this way, the first particle is moved to its new position in the first iteration. Let's go to the next particle. The current position of the second particle is here. What do you think the next position will be? To determine the next position, we refer to the PSO update equations. In the velocity update process, we need to calculate the three components: momentum, cognitive, and social. For this particle, we use separate random generators in the calculations for both the cognitive and social components. As we can see, we place the positions of these three components on the contour plot. The new velocity value is obtained by summing these three vectors: the momentum vector plus the cognitive vector, which is 0, and plus with the social vector. The sum of these vectors results in the new velocity vector. But the guard warns that the new value is not within the permitted range. Therefore, the new velocity value must be adjusted to fall within the permitted range, which is between -3 and 3. After updating the velocity, it's time to update the position. The new position vector is equal to the previous position vector plus the updated velocity vector. This new value falls within the acceptable range of -15 to 15 and is satisfactory. So, the particle will move to this position. Now that we know the new positions of the two particles, let's move on to the third particle. The initial position of the fourth particle is specified here, and its velocity is indicated here. Okay, now let's go explore the next position. First, the new velocity value is calculated using the updating equation. The first term represents the momentum component and is a vector aligned with the previous velocity, scaled by w, which is located here. The second term represents the cognitive component and is a randomly scaled vector aligned with the difference between the personal best position and the current position. Therefore, we can observe its location here. The third term represents the social component and is a randomly scaled vector aligned with the difference between the global best position and the current position. This scaled value is located here. The new velocity value is the sum of the three vectors: the vector of momentum component, the vector of cognitive component, and the vector of social component. Here the new value of the velocity is represented by this vector. Oops! This is not the end of the matter. The new value is outside the allowed range of -3 to 3 and needs to be corrected. According to this condition, the new velocity value is adjusted here. After updating the velocity, it's time to update the position. The new position vector is equal to the previous position vector plus the updated velocity vector. This new value falls within the acceptable range of -15 to 15 and is satisfactory. So, the particle will move to this position. Now that we know the new positions of the three particles, let's proceed to the fourth particle. We know initial position and velocity of the fourth particle. Now let's explore its next position. To calculate the next position, the new velocity component must be determined first. The new position can then be calculated accordingly. Based on the velocity updating equation, three terms need to be calculated. The first term is the momentum component, represented as a vector that aligns with the previous velocity and is scaled by w, which can be found here. The second term is the cognitive component, which is a randomly scaled vector that aligns with the difference between the personal best position and the current position. We can identify its location here. The third term is the social component, which is a randomly scaled vector aligned with the difference between the global best position and the current position. This scaled value is located here. By adding the three vectors including momentum component vector, cognitive component vector, and social component vector, a new velocity is obtained, which is represented by this vector. The guard checks the allowed range, and again this value is outside the range of -3 to 3, requiring correction. After applying the guard limitation, the new velocity value replaces the previous one. Now with the newly updated velocity, it's time to update the position. The new position vector is equal to the previous position vector plus the updated velocity vector. This new value doesn't fall within the acceptable range of -15 to 15. The second component of the position is outside the allowed range and will be corrected according to the R-guard conditions. Now that we know the new positions of the four particles, let's proceed to the last particle. Okay, as we can see in this contour plot, we have the current position and initial velocity of the particle, and we aim to determine the next position. As before, we will first consult the velocity update equation. The momentum component, which is represented as the scaled value of the previous velocity, is located here on the contour. The second part contains the cognitive component. The cognitive component of this particle is also 0 since we are in the first iteration and the particle lacks the experience of another individual. The final part, which includes the social component, is a randomly scaled vector aligned with the difference between the global best position and the current position. Since the global best in the previous time pertained to the fifth particle, its social component value also becomes 0. Now, we will combine these three components to obtain the new velocity value. With the other two components becoming 0, the new velocity for this particle is equal to the momentum component. The guard informs us that this value is outside the allowed range of -3 to 3 and needs to be corrected. Okay, now we will adjust it to fall within the allowed range. By adding the previous position value to the updated velocity, the fifth particle is moved to a new position, which also falls within our allowable range.